for doing this. I think it's really nice that we can post the whole class periods up there if anybody wants to review by looking over what happened in class. And thank you, Ed. Okay, so let's start talking about 4.9 Markov chains. And I guess I was going to turn the projector on, but that'll take so long. Let's just start talking about these things. There's only a few things from the handout that we need on the board here. So Markov chain is a pretty well-known use of linear algebra that has nothing to do with linear transformations, I would say. It has nothing to do with Rn and Rm or the geometry. So it's a kind of application of matrices and vectors that's really just about the numbers in an array. So it's from a very different perspective from what we've been doing. And what we're going to do is really very, very similar to that population example that we looked at in chapter 1. Really, that's just a special case of what we're doing right here. Okay? But we didn't use this language yet. Markov is the name of a famous Russian mathematician. I guess he had something to do with inventing this process. I'm not sure exactly what. So we need to have some words, some vocabulary. Probability vector is a vector that has no negative entries, and the entries add up to 1. So some examples like 0.4, 0.6, or 0.13, 0.75, 0.12. Those entries are probabilities, right? So you should have a little bit of understanding of probability theory. You don't need to know much at all for this example. But a probability is always a number between 0 and 1. Probability of 0 means something is impossible. Probability of 1 means something will definitely happen. Probability of 0.5 means it's 50-50, equally likely, equally unlikely, right? And then there's that whole range of probabilities from 0 to 1. But they always fall between 0 and 1. So these should look like probabilities, these entries in a probability vector, and that's why we call it that. A stochastic matrix is just a matrix whose columns are probability vectors. So there's an example there on the sheet. And on the handout, we also define a Markov chain, which is a sequence of probability vectors. So we'll denote it x0, x1, x2, so on and so forth. And along with a stochastic matrix, and it's the stochastic matrix that really is the glue that holds everything together, because what has to be true is that x1 is the stochastic matrix P times x0, x2 is P times the x1 vector, x3 will be P times the x2 vector. So there's this chain of events. And again, it should remind you of that population example that we looked at back in chapter 1. And there's a general statement there where x sub k plus 1 is always equal to P times x sub k. These guys are called state vectors. And I think the idea is that some system, something, is changing as we move from x0 to x1 to x2 it's usually going to be time changing. So as we move through time, the x sub k is a measure of the state of something. Okay. And let's look at this example. And I'm not going to write all this on the board. You can just read along with me on the handout. Sorry for my silly example. It's as creative as I get. If Mr. P had eggs for breakfast today, then there's a 20% chance that he will have eggs for breakfast tomorrow. And of course, that means there's an 80% chance that he will have no eggs tomorrow, right? If Mr. P did not have eggs today, then there's a 60% chance that he will have eggs tomorrow, 40% chance of no eggs tomorrow. So we consider that the given information, all right? And what we want to do is we're going to turn this into a Markov chain situation. And so in A, we're going to consider the situation if Mr. P had eggs today. So we know that's to be true. My Markov chain is going to be an x0 vector that corresponds to today. So x1 will be tomorrow. X2 is the day after that, and so on. And I'll be a little bit more precise here. So x0 will be a probability vector. And so its two entries, let's say, are the probability that Mr. P had eggs today, and the probability that Mr. P had no eggs today. And in the A situation, we're saying we know I had eggs for breakfast today. So that probability is 1, and the other probability is 0. Our x1 state, then, will be tomorrow, right? The probability of, I'm going to shorten my wording here a little bit and just say the probability of eggs tomorrow along with the probability of no eggs tomorrow. So there are just two entries. And I want to give myself some space here. And now here's where I'm going to get into a little bit of probability, but I don't think it's going to be anything that scary for you guys. Let's just think how we could break that down. We could say that I guess this one we don't need to do anything fancy with, sorry. Right, I think just from our given information, we know, where did I put my piece of paper down? So if he had eggs today, there's a 20% chance, or 0.2 chance that I'll have eggs tomorrow, and an 80% chance that I won't have eggs tomorrow. So I tend not to have eggs 2 days in a row, right? We can just fill that one in, x1. It's x2, the next day, where things start getting a little bit more complicated. Any questions about that? All right. So tomorrow I might have eggs and I might not, right? So the next day gets a little bit more complicated. Probability of eggs. Can we call this day 0, day 1, just so the subscripts match up? Probability of eggs on, then I can just say day 2 and avoid some of this, the next day, the day after that kind of talk. And the probability of no eggs on day 2. Okay. And here's where I think at this step we got to think a little bit about the way the probabilities would work, because at this point we don't know yet whether I had eggs or not on day 1. So we could say this probability, we could break it down in the following way. He had eggs on day 1, and he had eggs on day 2. Or, and I'll put that in parentheses, he had no eggs on day 1, and he had eggs on day 2. So that first entry has to be the probability that it's just referring to me having eggs on day 2. So either I had no eggs the previous day and I had eggs on day 2, or I had eggs the previous day and I have eggs on day 2. Those are the only two possibilities there, right? We broke it down into sort of like an and an or. And then there's a similar statement we could make about the probability of having no eggs on day 2. He had eggs on day 1, and he had no eggs on day 2, or he had no eggs on day 1, and he had no eggs on day 2. And we're going to simplify this in a bit, but I think we got to think about this first. Now, there's also some issues here about events being independent and probabilities not overlapping, but I think we'll be okay with this. I'm going to fill in some values. Now, I really mean the probability of these things happening, right? And now here's where a little bit of probability theory comes in. The probability that I had eggs the previous day is in that 0.2. That was right back here. Tomorrow is day 1. Sorry. Yeah, I'm sorry. I'm trying to not get too formal with the language. Today is day 0. So by the time we get to day 1, that's the day we're talking about, right? It's not the day after that day. So sorry. This is all I was referring to. Tomorrow just means day 1. That day. So the probability of he has eggs on day 1 is 0.2. That's the tomorrow day, right? The day after today. Now, and the probability of one thing happening and another is, if we assume independence here, and we are, that's going to be the product of the probabilities. So the probability that he has eggs on day 2 is going to be, well, if he has eggs one day, the probability that he has eggs the next day is going to be 0.2, right? Or when we have one situation or another situation, we can add the probabilities, all right? And again, I'm not getting too much into the probability detail here. I think you can go along with me. So we say he had eggs on day 1, which is 0.2. And he had no eggs on day 2. Well, if he had no eggs after a day of having eggs, the probability of that is 0.8. Okay, so I'm just trying to motivate where this line of probabilities is coming from, where I'm multiplying and adding. If he had eggs on day 1, there was a 0.2 probability of that, and he had no eggs on day 2, that's times 0.8, plus if he had no eggs on day 1, 0.8 probability, times if he had no eggs on day 2, another 0.8. And now what I want to do is I'm actually going to question?
So is it 0.8 or 0.6 if you didn't have X on day 1, didn't have X on day 2?
Oh, did I just mess up? I think I may. Oh, no, I did screw up. I did mess up. So, all right, I better. So we're not going to. I screwed up. I'm just going to back up, start over. All right. So my attempt to break this down into easy to understand language, I screwed up. So let's just go back to starting out. So the probability of eggs, if he had eggs on day 1, I do think that's 0.2. And if he has eggs the next day, I think that's going to be 0.2. If he had no eggs on day 1, so that's our 0.8. And if he had no eggs, the probability that he has eggs the next day is 0.6. Okay, so this is where I'm screwing up. So just look at the wording of my problem. If we have eggs on one day, the chance that he has eggs the next day is 0.2. If he has eggs for breakfast today, there's a 20% chance he will have eggs for breakfast tomorrow. If he had no eggs for breakfast the first day, there was an 80% chance of that. And if he did not have eggs one day, then the probability of him having eggs the day after a no egg day is 0.6. All right? It's from our statement. Yeah, thank you, Helena. If he had eggs on day 1, again, that's 0.2. If he had no eggs on day 1, by the way, those stay the same. But if he had eggs on day 1, then the probability that he has no eggs on the day after is 0.4. And if he has eggs, no eggs on day 1, again, that's still our 0.8. But from our statement, if he had no eggs on one day, then there's a 40% chance that he will have no eggs the second day. And now I think I'm still messing up. I'm just having a bad day here. If he had eggs on day one, then there's a 60% chance. So here again. All right, so I totally managed to screw up what I'm writing down today. All right, now what I want to say is that we can think of this as a 2 by 2 matrix times this previous state vector times my x1 vector. And have I lost everybody? I feel like I've lost everybody. Yeah, Ed? So if I had eggs on one day, okay, oh, so I think I had it right. Okay, sorry.
And then the number underneath it, though.
If he had eggs on day one, all right, then the chance that he had no eggs is 80. All right, so I'm sorry. I'm just totally spacing out on the obvious thing today. I want to cancel class and come back next time. We're not going to post this video. This is not tricky. I'm just totally tripping out on playing lost in my statement. So he had eggs on day one. Then we know it's 0.2 for eggs on day 2. If he had no eggs on day 1, if he had no eggs, the probability of eggs the following day is going to be 0.6. 0.6 is the probability of eggs after no eggs. If he had eggs the first day, the probability of no eggs is 0.8. These two guys go together, right? Again, if we have to go back to the first sentence, if he had eggs, the probability of no eggs the second day is 0.8. If he had eggs on day 1, if he had no eggs on day 1, that was 0.8. But then the probability of no eggs the following day is 0.4. Okay. All right, so as usual, I'm the last person to figure it out after you guys have everything. And what I want to do is I want to back up and think of this as matrix multiplication times a column vector. So I can think of this as going across a row times a column. This is going to be 0.2, 0.6, right? Going across and down will give me my first entry here. And 0.8, 0.4 will match up there. So much for my attempt to try to motivate this stochastic matrix. So sorry, I totally screwed up today. And it's not profound. I managed to make it something that's not pretty straightforward, confusing. The stochastic matrix here, the 0.2, 0.6, 0.8, 0.4, you can just think of, no, I don't. Well, I want to say today, tomorrow, but it's really from one day to the next day, all right? Either eggs or no eggs, eggs or no eggs. So notice how the setup of this stochastic matrix. This entry is the probability of eggs tomorrow if we had eggs today. This is the probability of eggs tomorrow, I hope, if we had no eggs today. This is the probability of eggs tomorrow if we had eggs today. This is the probability of no eggs tomorrow if we had eggs today. And this is the probability of no eggs tomorrow if we had no eggs today. Yes?
When we think of it more generally, the say that today and tomorrow is like day and day.
Yeah. And I will never say today and tomorrow again, because I was trying to just not get too formal, but it really isn't whether it's today or tomorrow or Wednesday or Thursday. It's just from one day to the next. And what is this, by the way? So x2, which is 0.2, 0.6, 0.8, 0.4, 0.2, 0.8 turns out to be 0.52, 0.48. So I'm not going to ask you to do these multiplications by hand. This is going to start getting really messy now as we work our way down the line. X3, the probabilities for the next day is just going to be the same stochastic matrix, 0.2, 0.6, 0.8, 0.4, times our x2 value, 0.2, 0.6, 0.8, 0.4, times the 0.52, 0.48. And I just want to show you that's 0.392, 0.608 are the probabilities. Okay. And what we're interested here in, is there any kind of trend? What is this going somewhere? Are these probabilities going to just head somewhere? Or are they going to stabilize in some way? And I'll put just a few of these down. Let's see, that's x3, x4 is 0.4432, 0.5568. x5 is 0.42272, 0.57728. x6, x7, x8, x5, 6, 7, 8. For x8, I'm getting 0.4289, 0.5711, rounded off. Well, I mean, it looks like we're getting like 0.43, 0.57, right? So the question is this stabilizing in some way? Are we heading toward a limiting value? And before we answer that, I want to go to the B situation on the handout, okay? And take this same problem, but start out with a different x0. So B is the same situation. Where, but with x0, well, we're saying compare the situation if there is a 70% chance that Mr. P had eggs for breakfast today. So if x0 is a 0.7, 0.3, say initial state, right? So from part A, I guess I'm suggesting pretty heavily that we are approaching some sort of limiting value. It seems like these numbers stop wandering around very much once we work our way down the line a bit. But what happens if you start out with a different initial state? So x1 will be the same stochastic matrix, so 0.2, 0.8, 0.6, 0.4 times 0.7, 0.3. So
Backing up, sort of, for x0, we knew you had it. Are we still assuming you had eggs on it?
pardon?
Is this just like the last one where we assumed that you did have eggs on day 0?
Yes.
So then, oh, okay, so isn't
So I guess in the first one, we were saying the probability of having had eggs today was 100%, and the probability of not having eggs today was 0% for today. Now we're saying, I'm not telling you, right? So all right, maybe I got to change my egg example. Maybe it's the eggs that are the problem. Breakfast, maybe. It should be lunch and not breakfast. So I haven't had my breakfast yet, so I'm still deciding whether I'm going to have eggs today or not. There's a 70% chance. So sorry if my choice of example isn't confusing. So we're just saying, suppose, again, we don't know what happened today yet. We don't know what the initial state would be. Suppose it's just a probability situation where 70% chance of eggs, 30% chance of no eggs. So again, try to see that even with this different starting state, the stochastic matrix is the same. I'm not going to dare try to write it out in words, but we're doing the same thing. Our probabilities are going to be 0.2 times 0.7 plus 0.6 times 0.7, 0.8 times 0.7 plus 0.4 times 0.3. All right, now I learned my lesson. Next time I'll write the matrix down first and talk about what it means first. Okay. Yeah. 0.3, yeah. I'm 0.2 times 0.7, 0.6 times 0.3. Yes, that's a 0.3. 0.8 times 0.7, 0.4 times 0.3. Okay. And actually here, too, notice I believe it's coming out that the probabilities are this is chance of eggs today, chance of eggs tomorrow, given that there are eggs today. So when I write it out this way, the day n is here. Day n plus 1 is here, I believe. So if I wrote it out in words, I would have these guys interchanged. 0.3 is the chance of eggs on day n. If they have eggs on that, of no eggs on day n, then the chance of no. Yes, then the chance of eggs the day after, if they had no eggs on one day, the chance of eggs the next day is 0.6. So this first line, again, is chance of eggs the day after. Second line is chance of no eggs. But just if you're trying to match it up with the days, if I use the matrix multiplication, the second day number's coming first here. And so what does this turn out to be? 0.32, 0.68 time. I'm just going to write down some values, right? So you see, as we go from one day to the next, x2 is 0.472, 0.528, x3 is 0.4112, 0.5888. I'll put an x6 value down is 0.4297, 0.5703. Now, I don't think it's totally obvious here, but are we approaching the same limiting value as in the previous situation? Same as part A. I mean, it kind of looks like that. And to me, that's the most surprising thing about this whole problem, this whole subject. We start out with a different initial state, different probabilities, and yet as we move from one state to the next, our limit appears to be the same. And it is the same. And that's one of the great results of Markov chain theory that we're going to come back to next time when we talk about the back side of the handout. And actually, let's just look at the top of the back side. So a probability vector Q is called a steady state or equilibrium vector if for a stochastic matrix P, if P of Q equals Q. Do you see what the meaning of that statement is? We know in our Markov chain, x1 equals P of x0, x2 equals P of x1, x3 equals P of x2, xk plus 1 equals P of xk, all the way down the line. This sort of stabilizing issue here is like, what if eventually we get to a value, we'll just call Q, where when we multiply by the stochastic matrix, we just get the same vector again. That's kind of like saying xk equals xk plus 1, xk plus 2, xk plus 3. Now, what's going to happen is we may never hit this value exactly, but we will approach it as a limit. So it's just like a calculus limit where we're going to get closer and closer and closer to the point where, for all practical matters, we're essentially there. But can we find Q? Such a Q. Can we find a steady state vector for the system? And I guess great way to leave you hanging. I better quit while I'm behind here today. And so sorry about that whole mix-up today. And it turns out this is not. It's not going to be that. Like, we know all the matrix theory now, where this is going to be no problem for us. But I'm not going to say how to do it till next time. And we will have this on our exam, so I won't put an egg problem on the exam. No. So I won't give you a word problem where the wording is so confusing that I can't even write down the system. Okay, so before we quit today, the question is, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So we're missing a few. Would you rather postpone the exam to the following Monday instead of a Friday? I really have, I'm okay either way. Who likes Friday? Who likes the following Monday? All right, it's too much of a split. We're sticking with Friday. So, well, Fridays again? It's too split. It's too, yeah. So we're going to stick with the original day. Sorry, I don't want to mess with the schedule if it's not a very close to unanimous decision. Apologies for today. Hate to ruin your Friday. I got a little confused.